I'm Dr. Donna Nelson at the University of Oklahoma, and this lecture is for my organic chemistry class. So this is going to be the first video for Chapter 19, Aldehydes and Ketones. And the PowerPoint that I've created parallels the textbook by David Klein, his organic chemistry textbook. And so in this chapter, we're going to have 4 filmed lectures that are devoted to this chapter 19, and you can see how they're divided here. So the first video, this lecture, covers the introduction, nomenclature, the preparation of aldehydes and ketones. A lot of this is going to be a review because you've had these sprinkled through other earlier chapters from this textbook. And you're going to see an introduction to the nucleophilic addition reactions that take place at these carbonyl compounds. So let's go ahead and start. So, ketones and aldehydes are similar in that they each have a carbonyl group. An aldehyde has one alkyl group attached to the carbon and one hydrogen. A ketone has 2 alkyl groups attached to the carbon bearing the double bond. The simplest aldehyde, formaldehyde, has 2 hydrogens attached to carbon. The simplest ketone has 2 methyls attached to carbon. And you can see this is used as a preservative, formaldehyde. I'm certain that you've heard of formaldehyde. And then acetone is used mainly as a solvent. We use it in lab extensively, very, very often. They're extremely important compounds. Ketones and aldehydes, here are some common ones that you may encounter as you go through your chemistry courses. So here is vanillin, cinnamaldehyde, carbone. Notice this is one of the optical isomers. This is an optically active compound, and it is one of the very few optically active compounds that you can actually discern by its odor or taste. So the R isomer of carbone smells like spearmint, and the S isomer smells like caraway. These are used frequently in class. They'll be passed through the class so that the students can differentiate, can become convinced that they can differentiate between these 2 optical isomers simply by their odors. And so they cannot be differentiated by melting point, boiling point, IR, NMR, by GC using most gas chromatographic columns. However, you can differentiate between the 2. There's about, I read 3% of the population cannot differentiate between the carbones. And it's very interesting and quite remarkable that you can differentiate. The optically active site inside your nose is such that it's like a glove, a hand fitting into a glove. One isomer will fit into the site so that you smell spearmint. The other isomer will fit into the site so that you smell caraway. So, and I had never noticed before I smelled these that there is actually a similarity in the odors of spearmint and caraway. So it's very, very interesting. There's also benzaldehyde, which has an almond flavor and a really nice almond odor. This molecule smells great. There's also progesterone and testosterone. So let's move on. So there's 4 discrete steps, at least, to naming an aldehyde or ketone. You're going to see some of these exemplified. Same procedure as with alkynes, alcohols, etc. Identify and name the parent chain. This is a little more complicated than it sounds right here. Identify the name of the substituents, the names of the substituents. Assign a locant to each substituent. Substituent means usually functional groups. Assemble the name alphabetically. And so let's look at some examples. It always helps to have examples. So for example, here's butane. You simply remove the E and replace it with al to name the aldehyde. This is butanal. So here's your aldehyde functionality, and the al tells you that it's an aldehyde functionality. Now normally, look at this parent group, this backbone, this alkyl chain here, 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 carbons in this, in this alkyl chain, and you have a 1 carbon substituent here. However, if there is a functional group attached to this carbon, that no longer becomes the parent. This is no longer the parent. The parent must always contain the highest priority functional group. So this molecule only has 1 functional group, and that is this aldehyde functional group. And so the parent must contain that functional group. So now you have to identify the longest carbon chain that contains that functional group. So now, instead of going out on this propyl chain, we go up onto this carbon that bears the carbonyl. So now it is a 1, 2, 3, 4, 5, 6 carbon chain. And you, of course, will start numbering up here at the functional group. So you would number this 1, 2, 3, 4, 5, 6. So it's hexanal. So this is going to be 1, 2, 2-propyl hexanal. And so that's the way that you name that molecule. So now, here is an interesting example. This example has 3 functional groups. You can number down the alkyl chain either from the left side, 1, 2, 3, 4, 5, 6, 7, or from the right, 1, 2, 3, 4, 5, 6, 7. And so one must determine here which of these functional groups has the highest priority. Is it the alkene, the alcohol, or the aldehyde? And the aldehyde is the highest priority functional group. The second highest priority functional group is the alcohol, but that doesn't matter here. You identify the highest priority functional group and start numbering there. And it doesn't matter the priorities of any of the others, but I'm just telling you, this would be highest priority if you did not have the aldehyde. So we start numbering here. This is correct as shown. 1, 2, 3, 4, 5, 6, 7. Incorrect over here because you don't want the highest priority group to have the highest number. You want the highest priority group to have the lowest possible number. For ketones, you replace the E with O-N-E. So butane becomes butanone. So here it's not necessary to put the 2 because butanone the carbon-oxygen double bond must be at the 2 position. It can't be at the 1 position because that would be butanol. It can't be at the 3 positions because if it were over here, you'd just start numbering at the other end of the molecule. 1, 2, 3, 4. So there will not be a 1-butanone or a 3-butanone or a 4-butanone. There will only be 2 butanones. So you don't need to put the 2. It's understood. So here we have, in the next one, you see that this is heptanone. It is a 3-heptanone, and usually it is named 3-heptanone, unless you have other functional groups in here where you're going to have to give the locant of the other functional groups, and those locants would need to also go at the front of the molecule. And in that case, if you have other locants that must go at the front of the molecule, the 3 is moved inside and put just before the ONE so that it doesn't become confusing which locant refers to which suffix. So 3-heptanone is what is typically given for this molecule, but heptane 3-one would be appropriate as well. The configuration of the chiral center is indicated at the beginning of the name. So you can see here R, 2-chloro, 1, 2. 3-phenyl, 1, 2, 3. Phenyl, propanal. So here you can see the way this name is constructed. Aldehyde next to a ring is named as a carbaldehyde, cyclohexane carbaldehyde. IUPAC recognizes these common names: formaldehyde, acetaldehyde, benzaldehyde. Let's see if I missed. Yes. Okay, so now a review of some of the reactions that will yield aldehydes. So the ozonolysis of alkenes from chapter 8, you remember that if it is an alkene such that you have a CH bond attached to the carbon, this is going to generate the aldehyde, okay? And so here you see that the ozonolysis cleaves the carbon-carbon double bond. If you don't remember this, then go back and review in section 8.12. Hydroboration, oxidation of terminal alkynes will give the aldehyde also. And so here you have the carbon-carbon triple bond, that becomes the carbon-carbon, and this carbon is a carbonyl. This comes from section 9.7, hydroboration, oxidation. You can go back and review this. This is always also in Klein's textbook. Another review from this same textbook, oxidation of secondary alcohols. This is for ketone preparation. If it's a secondary alcohol, you're not going to have an aldehyde. You're going to have the 2 alkyl groups attached to the carbonyl carbon, and that will be a ketone. Ozonolysis of alkenes in which you do not have a CH bond, but both of the bonds attached to the sp2 hybridized carbon are alkyl groups. So here we have ozonolysis, and remember ozonolysis simply cleaves that bond, and so you have 2 ketones. This you can go back and review if you don't remember it. Acid catalyzed hydration of terminal alkynes. So now you have this carbon-carbon triple bond Instead of hydroboration, you have the acid catalyzed hydration using the mercuric sulfate. And so this gives the internal carbonyl as opposed to the terminal carbonyl. The hydroboration oxidation gave the terminal carbonyl. This gives the internal carbonyl. And so that means the internal carbonyl is, of course, going to be a ketone. That comes from section 9.7 of this same textbook, Klein's textbook. Another reaction, the Friedel-Crafts acylation, which you just saw in the last chapter, section 18.6, you will remember that when you react benzene with carboxylic acid chloride and aluminum trichloride, that attaches the carbonyl to the benzene ring, and now you have the ketone. Remember, the carbonyl carbon has resonance structures because the carbonyl carbon is very highly polarized. Oxygen is highly electron withdrawing. It's highly nucleophilic. It has the, it is next only to fluorine in its nucleophilicity. And so the parabolic, the pi electrons, remember, are very loosely held. They're not held closely to the nucleus. And so the pair of electrons, the pi electrons, can move out onto oxygen. They spend a lot of time out on oxygen. They spend more time on oxygen than they do on this carbon, and that gives the oxygen a partial positive charge, a partial negative charge, and the carbon will have a partial positive charge. So this arrow indicates that the pi electrons, as well as the sigma electrons, but the pi electrons to a greater extent are polarized onto oxygen. They actually spend more time on oxygen than on carbon. And so the pi electrons are more highly polarized than even the sigma electrons. These two resonance structures indicate that. Here, this structure indicates it. That resonance is going to demonstrate the effect upon the pi system. Induction is a term that discusses the sigma system. So this refers to really exclusively the electron withdrawal through the sigma bond. So you have oxygen withdrawing electron density from carbon through the pi system as well as through the sigma system. And so the resonance, and what is drawn here, indicates the electron withdrawal conjugatively, and this indicates the induction through the sigma system. So they both contribute to the greater negative charge on oxygen and the partial positive charge on carbon. The carbonyl group is planar, and you have an sp2 hybridized carbon here in the carbonyl group. That means that the carbon and this carbon that are bonded to that carbon are coplanar with the carbon-oxygen bond. All four of these atoms are planar. So this is classified as trigonal planar. The nucleophile that comes in for attack at the carbon, which is bearing the partial positive charge, the pair of electrons moves out onto oxygen. So the nucleophile that comes in for attack at the partial positively charged carbon could just as easily come in from the bottom. So the two faces of the this carbonyl system are equivalent in most reactions. And so you see the nucleophile comes in from the top. It could have just as easily come in from the bottom. One side is not preferred over the other. So this sp2 hybridized carbon and the planar molecule they are converted to an sp3 hybridized carbon and a tetrahedral molecule. Aldehydes are more reactive towards nucleophiles because of steric effects. For one thing, aldehydes have only one alkyl group attached to the carbon in each molecule. The other one is hydrogen. As you know, the hydrogen is going to be much smaller than any alkyl group. The ketone will have two alkyls, so this is going to be bulkier around the carbon, which is the site of attack. The carbon is bearing a partial positive charge. This carbon is bearing a partial positive charge. The alkyl group is electron donating. Each alkyl group is electron donating, more so than a CH bond. And so the partial positive charge here on the carbon will be partially satisfied by electron density being donated from two alkyl groups. This partial positive carbon will be partially satisfied by one alkyl group donating electron density to carbon. And so the aldehyde is going to bear a lower partial positive charge than the ketone. And so the aldehyde will be more reactive because of the electronic effects and also because of the steric effects. So that's very logical. That should be easy to remember. Some nucleophiles require acidic conditions. If they're just not very strong nucleophiles, even if they're in the presence of a carbonyl, they will not react. And so the reaction will need to be catalyzed, usually by the addition of a small amount of acid. Others will require basic conditions. An example of one that must be run under basic conditions is a Grignard reaction. And the reason it must be run under basic conditions is because this Grignard reagent, if a small amount of acid is added to this Grignard reagent, the Grignard will simply react with the acid. The methyl, remember this is the equivalent of Me minus, the methyl anion. That will simply be protonated and it will destroy the Grignard reagent. So here, the reason that it must be run under basic conditions has nothing to do with the carbonyl, it has to do with the reagent. And so a strong nucleophile is usually going to be easily protonated. And the strong nucleophile, if it's like hydroxide or methoxide, if a small amount of acid is added to that nucleophile, it will simply be protonated and the reagent will be destroyed. So if you have a strong base or a strong nucleophile, something that will react like a strong base, like this Grignard, it will need to be run under basic conditions. So we're going to see examples of reactions at the carbonyl which must be run under acidic conditions because the nucleophile is simply too weak, or it may need to be run under basic conditions because the nucleophile will react with protons. So we'll see both of those examples. Under basic conditions, if the nucleophile is strong enough, it simply attacks one side, one face of the carbonyl, either coming in from the front or coming in from the back. Here, this has been turned so that it looks like the nucleophile is coming in from the side. And that will happen if this carbonyl is turned. So you have a nucleophilic attack. pair of electrons attacks at the carbonyl carbon. The pi electrons move out onto oxygen, generating a negative charge on oxygen. And so you have formed a carbon bond to the nucleophile, whatever it is. And then this reaction needs to be neutralized by simply quenching it with a small amount of water, or you could use a small amount of dilute acid. So whenever you have the nucleophile attack, you'll generate an anion, and then you'll have to neutralize the reaction so that you can have the neutral product formed. So this gives information. You have just seen information about the reaction of carbonyl compounds under basic conditions. In the next lecture, we'll go on to look at the reactions of carbonyl compounds under acidic conditions.